Let us begin our today's session on Riemann integral or Riemann integrability. So the objective of today's session will be on the definition and its concept. We can simply call it as Riemann's definition of integral, and then we take some problems. Later we discuss about some standard results which are useful in solving the problems. Later again we move to the problem solving sessions. So this I have planned for today's session. Okay, so please take a note of it. Then we will start our session. After noting, please tell. Right. So if we consider a definite integral, let us say integral a to b f of x dx. So what is the geometrical significance of this one? Where f of x is a single variable function. Can you say? So if you are calculating integral a to b f of x dx, any idea for anyone? So bounded region between a and b, in other words, can we assume that if this is the function, this is a and this is b, so you are going to calculate the area bounded by the curve and the axis between a and b. Do you agree? Right. Anybody has any query over this one? If you consider the definite integral. Fine. Now what happens? Our main intention is nothing but calculating this bounded region. So in the previous classes, you have heard about the word that is partition. Nothing but whenever you consider an interval AB, we will select randomly some points between A and B. Selecting the points is at random, it is our own choice. And in other words, you are bifurcating this interval, usually equal intervals. In other words, you are taking the segments like this. So if you calculate the area of each segment and sum up all these segments, will it give the area of the required function? Say. So the Riemann's concept is based on this criteria. Whenever you are considering a partition on the given interval, it is nothing but you are selecting randomly some of the points here. How good you choose the points between A and B, and you are going to calculate the each segment value. Usually it looks like a trapezium or rectangle, and summing up all these things will give the area bounded by the axis and the curve. Clear? Now let us go with the mathematical orientation for it. So usually whenever we are calling about the integration concept, we always take f as a bounded function. If f takes infinite value, you cannot integrate the function. So always we talk about a bounded function and its integral value. Now what happens? We will take a partition a is equal to x naught, x1, x2, so on, xn is equal to b. So how many points I have taken here? I have taken n plus 1 points. So obviously I will get n small subintervals. So the first subinterval is nothing but x0, x1, nothing but a comma x1. Second subinterval will be x1, x2, and so on. The last one will be xn minus 1 comma xn, nothing but xn minus 1 comma b. And for each subinterval, we will calculate the length. The length is nothing but the difference between the endpoints. Here x1 minus x0, here x2 minus x1, and so on. So the length of the subinterval we usually indicate with delta. So delta 1, delta 2, delta 3, so on, delta n. So delta 1 indicates first subinterval length, delta 2 indicates second subinterval length, and so on. Delta n indicates nth subinterval length. Whenever you choose an arbitrary subinterval, say delta r, it is the length of the interval x r minus 1 comma xr. Is it clear? So please take a note of it. Now, whenever we consider a partition on the interval, obviously the function f takes usually different values. So you can calculate the smallest value and highest value for the function, nothing but infimum and supremum for the function. It is possible to calculate the infimum and supremum for the small subinterval 2. Accepted? We are going to calculate the smallest value and biggest value for the function on the subinterval what you have taken there. So for that, we indicate that whenever you take the rth subinterval IR, its infimum will be denoted by MR and the supremum will be denoted like this, capital MR. Now why we are doing all these things? Earlier at the plus 2 level, you have learned that integration is nothing but a sum. Similarly, here we are going to define two sums. First one is called lower sum. Second one is called upper sum. And how we are defining this sum? You consider a function on the closed interval AB. You have taken a partition randomly here, and for each subinterval you have taken that this is the infimum and this is the supremum, and the length of the subinterval is indicated as delta r. Now the lower sum is defined as LPF. F is nothing but the function what you have taken. P is the partition, what are the partition you consider on the interval. L indicates lower sum. It is defined as summation r is equal to 1 to n small mr delta r. So what you are doing, you are multiplying the infimum value with the length of the subinterval and you are summing up all these things. It is called lower sum. You can call it as lower Riemann sum. Similarly, you define upper sum. UPF is equal to summation r is equal to 1 to n capital MR delta r. Is it clear now to all how the sums are defined? Say. Now let us take a simple example so that you can understand what are these sums. Right? Now, for our convenience, let us take a simple function, say f of x is equal to x square. You just give me a closed interval. Give me two numbers. Right? So let us take the interval as 2 and 7. A value is 2, B value is 7. Now you are taking a partition on this. Now you can take randomly any number of points between 2 and 7. Let me say I am going to take 2, 3, 3.5, 4, 6, 7. Is it acceptable to you? Now what are the subintervals I am going to have here? 2, 3, 3, 3.5, 3.5, 4, 4, 6, and 6, 7. These are the subintervals I will get here. Now, for each subinterval, if you calculate the function values using x square, you will get infimum as well as supremum. So, since x square is an increasing function, the first number 2 gives the infimum and second number 3 gives the supremum here in this case. So here infimum f here is equal to 4, 2 square is 4, and supremum f is equal to 9. So you are going to calculate for each and every interval here. So you can call it as, this is the first interval I1, so this is M1 and this is capital M1. If you consider the lengths, here the difference between these two is 1. So delta 1 is equal to 1. Here delta 2 is equal to 0.5. Here delta 3 is equal to 0.5. Here delta 4 is equal to 2. Here delta 5 is equal to 1. Now, can you visualize how I am going to calculate the LPF and UPF? So if you are going to calculate LPF, it is nothing but M1 delta 1 plus M2 delta 2 plus M3 delta 3 plus M4 delta 4 plus M5 delta 5. Since I have taken 5 subintervals here. So if you sum up all these values, you will get a number. This is called the lower sum. In the same manner, we can calculate the upper sum UPF, multiplying with the supremum values with corresponding subinterval length. I think it is not necessary for you to calculate the value. You have understood how to calculate that. Say. Right. Now, after calculating LPF and UPF, what are the partition you consider usually? Always the lower sum is less than or equal to upper sum. What are the function you consider? Always lower sum will be less than or equal to UPF. The lower sum will be less than or equal to the upper sum. Now, one interesting thing here is the sum is based on the partition, isn't it? So, if the sum changes means the partition is changed, because we can select a partition on the interval in infinite number of ways. This is the partition I have selected here. You can take the other partition as 2, 4, 6, 7. It is also a partition on the given interval. Accepted? Yes or no? So if you calculate LPF and UPF, obviously the value will be different. So what you are trying to do here is, for different partitions taken on the interval, you are having different lower sums and different upper sums. Now the concept of Riemann integral says that you consider all possible partitions on the interval which you have taken. Now, we define two integrals here. One is called lower Riemann integral. That's why in the suffix bottom we put a bar. Second one is called upper Riemann integral. So for the upper limit we indicate with a bar. So integral a bar to b and integral a to b bar. And the lower integral is defined as, for all the lower sums, you take the biggest among them. Similarly, the upper Riemann integral is defined as, for all the upper sums, you take the smallest one. So you consider all possible partitions on closed interval AB. So for all the lower sums, you take the biggest among the lower sums. So supremum of LPF, we call it as lower Riemann integral. And here, for all the upper sums, you take the smallest among them, we call it as the upper Riemann integral. If these two values are equal, that is integral a bar to b f equals to integral a to b bar f, then we say that the function is Riemann integrable. Since the two integration values are equal, you are going to get a number. So it is called the Riemann integral value of the function f. So the bar will be removed, and generally we indicate that integral a to b f is equal to some number. Always we will have the lower integral value is less than or equal to the upper integral value. That is by default true. We will have a result also that is immaterial with respect to the class session. So always the lower integral is less than or equal to upper integral. So whenever the two values are equal, we say that the function is Riemann integrable, and we denote the common value as integral a to b f. So this is the total concept of the Riemann integral. Clear? In other words, we can call it as the Riemann's definition of integral in other way. Now, if you think about the sums, lower sums and upper sums, what we can understand geometrically if you draw a picture. So, this is my thinking. Let us discuss on that. Suppose this is the graph you have taken for the function f, and this is the interval AB, and you are going to integrate the function. In other words, you are going to calculate the area bounded by the curve and the x-axis. Integral a to b f you are calculating. Now, if you have taken a partition on the interval, means randomly you have selected some points here, so that you have some segments here. So selecting a partition is arbitrary, so you can take so many number of segments between A and B. That is up to you. So for our convenience, I have taken 1, 2, 3, 4 segments here. Now, for each segment, so if you understand that this is the function's highest value, this is the function's lowest value, accepted on the graph. So if you say for the first interval delta 1 is nothing but difference between the endpoints. So it is nothing but you are taking the breadth here. This horizontal width you have taken. So if you take, say, m1 delta 1, so what does it mean? You are going to have a rectangle here, length into breadth you are doing. Is it clear to you? M1 indicates the length, delta 1 indicates the breadth. So in this way, m1 delta 1 plus m2 delta 2 plus m3 delta 3 plus m4 delta 4, if you will do, so you have approximated the area of the region by means of rectangles. Clear? Similarly, if you take the upper sum, so capital M1 delta 1, capital M2 delta 2, and so on, again you are going to get the area by means of rectangles where the upper values are considered. So whenever the lower sum and upper sum are equivalent, then automatically lower integral and upper integral will be almost equivalent. Accepted? So this is the idea behind the Riemann's definition. Any more queries to anyone? What are the concept? If you have any doubts, you can ask. We will discuss on it. Have you studied this concept earlier? Any one of you or all of you? Have you studied this Riemann's definition earlier? Right. Now, see the thing here. Here I have taken one partition. Corresponding that, I have approximated area by means of it. Agreed? Now, you can choose a different number of partitions, right? Now, what happens for the same curve? I have taken so many number of segments. Here also, I am taking the same path like m1 delta 1 plus m2 delta 2 plus so on plus mn delta n if I have taken n subintervals. Here also I am going to get the area of the region by means of summing up the rectangular areas. Accepted? So here the question raises that what is meant by supremum of LPF? Because selecting a partition is infinite ways possible on a subinterval. So it is nothing but if you have considered all possible segments between A and B, in other words, without leaving any single point between A and B, if you have considered all the points between A and B, automatically that will be nothing but the supremum. Agreed? The maximum possibility of the lower sum you have calculated. So it is nothing but, generally we will write the partition as A is equal to x0, x1, so on, xn is equal to b. Nothing but you have divided the AB interval into n segments. So what happens if n tends to infinity? In other words, you have bifurcated the interval into infinite parts. Nothing but all minutest points you have considered between A and B. Then also if you perform the same sum, whether you take the lower one or upper one, so it will be nothing but approximating the region exactly. So LPF is nothing but sum of the region taken by infimum of the function value here and subinterval length. So for each partition you will get one LPF. So among all the LPFs, you are taking the biggest among them. Let me say I have taken 3 partitions on the interval AB. So for the first partition, you calculate LPF. Second partition, calculate LPF. Third partition, you calculate LPF. Among the 3 LPF values, you choose the big one. That is called supremum of the LPF. Okay? Since choosing how many partitions are there between A and B, it is not practically possible because there are infinite number of ways to select a partition. So in other words, we are saying that you are going to bifurcate the interval AB into infinite number of segments, nothing but all possible segments you are considering. That is the underlying idea here. So usually what we write, LPF is nothing but summation r is equal to 1 to n mr delta r. This is function's infimum value on the subinterval This is length of the subinterval, and the total interval is bifurcated into n parts. Now what happens if this is infinity? What about LPF? We can say you have approximated the entire region by means of lower sums, the lower values of the function. Say, are you getting the idea or not? LPF value will vary according to the partition, because delta value is based on partition, isn't it? So LPF values, UPF values are based on partition. Since a partition is not unique, so we take the delta which gives us maximum. Let me say a simple thing. Let us take the function as f of x is equal to x itself. Take the interval AB is equal to 5, 10. The simple example. Now, if you take a partition, let us say 5, 6, 7, 8, 9, 10. So what will be delta? In each case, delta is 1. Because 5, 6 is length is 1, 6, 7 length is 1, 7, 8 length is 1. Now, what about the function value? Supremum and infimum, if you calculate for the first subinterval 5, 6, supremum is equal to 6, infimum is equal to 5 as per the function value is considered. So we are calculating f of 5 and f of 6. And what you are doing, if you calculate the lower sum, 5 into 1 plus 6 into 1 plus 7 into 1 plus 8 into 1 plus 9 into 1, you are doing. You will get a number. Accepted? Here delta is equally distributed. Similarly, if you calculate the upper sum, you are taking upper sums. 6 into 1, 7 into 1, 8 into 1, 9 into 1, 10 into 1. You will get the upper sum. Now what happens? Let us change the partition. So for 5 and 10, you take the partition as 5, 7, 9, 10. Now what happens? Delta changes, automatically LPF and UPF changes. Accepted? So that is what I am saying actually, because choosing a partition is not unique. So apart from choosing different partitions, which is not practically possible, considering all kinds of partitions on the given closed interval, apart from it, if you choose each and every point and you are calculating LPF and UPF, it is nothing but finding the lower integral and as well as upper integral. Okay? Are you getting the idea? Underlined idea. So I am considering each and every point between the interval. That's why I am saying n tends to infinity. The number of segments, I am taking infinite segments between A and B. However, the function values will be changing. Infimum and supremum will change. So the lower integral and upper integral will be defined as limit n tends to infinity LPF, and upper integral will be defined as limit n tends to infinity UPF. Whenever these two values are equal, you are getting a single unique number, that is called the integration value of the function. In this way, the concept is defined earlier by Riemann. Later, Lebesgue modified that, but we are just reading about Riemann integral only and its properties. So, there is one important result that whenever we take n tends to infinity, but for upper we have to calculate infimum. Please understand that you are calculating infimum if there are so many upper sums. If there is only one upper sum, it is nothing but there is no need to calculate infimum, right? Say, Let me say one thing. Suppose I have a interval AB. On this interval AB, I have chosen 10 partitions. So what is meant by a partition here? You are randomly selecting some points between A and B. So whenever you take any two partitions, there may be some points common or all the partitions are different. Now, for each partition, I will calculate the lower sum as well as upper sum. L P1F, U P1F, L P2F, U P2F, and so on. Now what happens? After finding all lower sums, I am taking the biggest among them. LP1, LP2, LP3, so on, LP10. All the lower sums, I am taking the biggest. Similarly, for all the upper sums, I am taking the smallest, infimum. Whenever these values are equivalent, if they are almost equal, then we said that the function is integrable. That was the idea. Now the question is that how can you confirm that there are exactly 10 partitions on the interval? There may be so many, isn't it? That's why we are saying that apart from limiting that only this much number of partitions are available on the interval, I am taking each and every point. So that what happens, there will be only one big partition which gives the LPF as well as UPF for calculation purpose. If the two values are equal, then we say that the function is integrable. Okay? Is it giving the idea or not? Or did you stuck anywhere? So if you have any more doubts, you can ask. No problem. So here infimum and supremum are nothing but after calculating all the sums, from all lower sums, you are taking the big. From all upper sums, you are taking the smallest among them. If they are equal, you are saying that the function is integrable. That was the idea. But the question raises that how many partitions you are going to choose and you can confirm. Because there are so many ways to select a partition on an interval. That's why apart from limiting ourselves that only this much number of partitions I am considering on an interval, I am taking the total big partition, nothing but all possible segments I am considering on the interval. So there is no need to find and search for another partition. So whenever we take n tends to infinity, we will get supremum of LPF and infimum of UPF automatically. That's it. Because as and when the number of points increases, the function value also increases, supremum of LPF, isn't it? That's it. That was the idea. Since we are just understanding the concept, how the integration is defined, since question will not be asked on this, problems are different. Now, there are some observations that suppose you have taken n segments on the interval, so you will have n subintervals, respectively their lengths are delta 1, delta 2, so on, delta n. So if you sum up all these lengths, you will get the main interval length, that is b minus a. So if you have a doubt, you can check for that. Take the interval 5, 10. Let us take a partition 5, 7, 9, 10. So here you will get delta 1. This is first segment, length is 2. second segment delta 2 is equal to 2, third segment 1. Now if you sum up all these values, the number is 5, nothing but main interval length 10 minus 5, 5. Okay. So delta 1 plus delta 2 plus so on plus delta n, summing up all the subintervals length, you are going to get the main interval length. So the general notation is summation r is equal to 1 to n delta r is nothing but b minus a, the main interval length. And now what happens, as and when the number of points are increasing, the points you are choosing between the values 5 and 10, the interval values, here we are going to find one interesting thing, that norm. What is meant by norm of the partition? So norm is indicated with the symbol. So whenever you take a partition P on closed interval AB, we say that norm of the partition is denoted by norm P, and it is defined as the maximum among the subinterval lengths. Suppose here I have taken 3 subintervals. First interval length is 2, second subinterval length is 2, third interval length is 1, among which the maximum length is 2. So norm of the partition is equal to 2. Suppose you have taken the partition with equal values, let us say 5, 6, 7, 8, 9, 10. This is the partition I have taken. So here interval length is 1, interval length is 1, interval length is 1, so on. So what will be the norm here? Norm of the partition is equal to 1. Accepted? In this case. So as and when the number of values goes on increasing, norm will be tending to 0. If I have taken, earlier I have taken n segments, if I have taken infinite number of segments, the norm of the partition will be tending to 0. So that thing we should know. Right? So on the whole, if we sum up our discussion, Riemann integral is nothing but you are going to calculate two integrals, lower integral and upper integral. Whenever these two values are equal, we say that the function is Riemann integrable. If the values are unequal, it is not Riemann integrable. Okay? That is the whole idea. And you are approximating the area bounded by the curve and the axis. As and when we understand that integral a to b f of x dx is giving what? And it is approximated by means of summing up the areas by means of rectangles. Okay? That is the whole discussion. So any more questions for anybody over this? If any questions you have, you can ask. Then I will move to some problem solving techniques. There we can discuss what are the approach in solving the problems. Shall I continue? Right. The fundamental criteria here is, if we are talking about the integrability of a function, the fundamental thing is the function must be a bounded function. then only we talk about this partition, lower sum, upper sum, equivalency, etc., etc. If the function is not bounded, then we say that we are not talking about its integrability. Now, there are certain results which are useful in proving that the function is integrable. So here also in learning the concept, we are not interested in finding or evaluating the integral value. Here we are interested that whether the function is integrable or not. That was the idea. So if the function is integrable, what could be the possible integration value? What is the lower and upper value? Between what values the integration value will come upon, etc., etc. We are going to discuss. And what are the other theorems useful in finding the integration value? So one thing is, if the function is continuous on closed interval AB, so I have a function on the closed interval AB. If I know that, or if I prove that the function is continuous on the interval, then it is Riemann integrable. So symbolically, we will write it as f belongs to R of AB. So R stands for Riemann integrable. So f is Riemann integrable on the closed interval AB. Another useful result is the function should be monotone. That means either it will be increasing or decreasing over the subinterval. Then f will be Riemann integrable over that interval. Another thing is, if it has a finite number of discontinuities, over the subinterval. Another thing is, if it has infinite number of discontinuities with a limit point. That means whatever the points of discontinuities we have considered, they should be tending to a limit. So these are some useful results. And another one thing that the result says that if the function is Riemann integrable, then for epsilon greater than 0, there exists delta greater than 0 such that the difference between upper sum and lower sum is less than epsilon. In other words, difference between upper sum and lower sum is almost equal, where the partition has norm less than delta. These are some useful results which are useful as and when we are doing some kind of problems, right? And these things are some criteria in verifying that whether the function is Riemann integrable or not, but these are always not necessary. Fine. So please take a note of them. Then we will take some interesting problems and we will discuss on it. Now let us take a problem that if f from closed AB to R is a constant function, then f is Riemann integrable. Let us prove this problem using the definition of Riemann integral. So please take a note of the problem. So I have taken a function f which is a constant function on the closed interval AB, and my intention is I am going to show that it is Riemann integrable on the interval what I have taken. Okay. Is it clear? The objective of the problem? Right. Now, following the diffusion method, let us take a partition on the interval, say so this is the partition I have taken on the interval AB. So whenever you take a subinterval IR, the rth subinterval, its points are xr minus 1 comma xr and its length is delta r. And obviously I have taken a constant function, so let us take that f of x is equal to k for all x belongs to the interval because it is a constant function. So in this case, what is the infimum and supremum for the function f? What is infimum of the function and what is supremum of the function? K itself, because whatever the value you take, the maximum value is nothing but k. So if you take any subinterval, its infimum is nothing but k, its supremum is nothing but k. In other words, the maximum function value on the subinterval is nothing but k. The minimum function value on the subinterval is nothing but k. Agreed? Right. Now, let us calculate the lower sum as well as upper sum. So, if we calculate LPF, it is nothing but summation r is equal to 1 to n mr delta r. Here small mr stands for infimum of the function over the subinterval IR. So this is equal to summation r is equal to 1 to n k into delta r, because the function takes only one value k, so infimum is nothing but k, supremum is nothing but k. Since k is a constant, it is not varying here, so k into summation r is equal to 1 to n delta r. So here we are summing up all the subinterval lengths. It is nothing but main interval length, so this is equal to k into b minus a. Any questions over this LPF? Similarly, if you calculate the upper sum, then also we will get the same thing. The upper sum value is also nothing but k into b minus a. So whatever the partition P you will take, always you will get lower sum as k into b minus a. Always you will get upper sum as k into b minus a, because the function is a constant function here. So if you calculate the lower integral, integral a bar to b f, it is nothing but supremum of all the LPFs. It is nothing but supremum of the value k into b minus a, nothing but k into b minus a, because it is a number. Similarly, if we calculate the upper integral, infimum of UPF, it is also nothing but k into b minus a. So lower integral and upper integral, both the values are equal, hence the function is Riemann integrable, because lower integral value is nothing but k into b minus a, and upper integral value is nothing but k into b minus a. Hence the function is Riemann integrable, because both values are identical. Clear? Is the solution approach clear, or do you have any queries? Please take a note of it. After noting, please tell. Right? So if you calculate the lower integral, its value is k into b minus a. If you calculate upper integral, its value is also k into b minus a. Since both values are equal, that is lower integral is equal to upper integral, hence the function is Riemann integrable. And the value k into b minus a is nothing but the integration value. Okay? And you can verify that. Let me say if you have taken integral 1 to 2 5 dx, what we will do? 5 into x, 1 and 2 is nothing but 5 into 2 minus 1. Accepted? The integration process usually we do. It is just like k into b minus a, the method. Agreed? For the constant function. That's it. So another thing is, suppose we have the function f from R to R or f from closed AB to R defined by the function f from closed AB to R is defined like this. F of x is equal to 1 where x is rational. F of x is equal to minus 1 if x is irrational. So here also we are going to verify whether the function is Riemann integrable on closed AB or not, using the definition of Riemann integrable. Okay? Please take a note of the problem. The function which you have defined here, say when x is rational, the value is 1. When x is irrational, the value is minus 1. This kind of function, we call it as Dirichlet function. It has the name Dirichlet function. After noting, you please tell. Right. Now, as usual, we will take a partition on AB. Say capital P is equal to A equal to x0, x1, x2, so on, xn is equal to B. And if you take any subinterval IR, the values are xr minus 1, comma xr, and the length of the subinterval is delta r. Now what happens? Whatever the partition you take, since the function is defined as 1 and minus 1, so infimum of the function is nothing but minus 1 and supremum of the function is nothing but 1. Agreed? Because the function takes only two values, 1 and minus 1 only. It is not going to take any different value. So whatever the subinterval you consider, first interval x0, x1, second interval x1, x2, and so on, rth interval. So whatever the subinterval you consider in the partition, the maximum value is nothing but 1 and the minimum value is nothing but minus 1, because the subinterval contains so many rational points as well as irrational points. So what happens, if you take the infimum small mr, it is nothing but minus 1. If you take supremum capital MR, it is nothing but 1. Agreed? Whatever the subinterval you consider, either first interval, second interval, third interval, and so on, last interval, the smallest value is minus 1 and biggest value is 1. Yes or no? say. So if you consider, yes, please understand, you are writing MR is nothing but so if I write M1, it is not that I am taking the endpoints. You are considering all possible points in the subinterval you have taken, and you are considering all the function values in it, among which you are picking which is small, which is big. The smallest is infimum and biggest is supremum. So if you imagine the graph, let me say this is one subinterval, this is one subinterval. Here I am taking the function value. I am calculating f of something. This is the biggest value of the function. This is the smallest value of the function. Let me say biggest value is given by y, smallest value is given by x. So f of x is nothing but infimum, f of y is nothing but supremum. That is the thing actually we need to understand. We are not considering about the endpoints. So small mr gives the smallest value of the function on the subinterval. Capital MR gives the biggest value of the function on the subinterval. Okay? In other words, we are calculating function values on the subinterval. Fine. So let us calculate the lower sum as well as upper sum here. So if you consider LPF, summation R is equal to 1 to n MR delta R. This is equal to summation R is equal to 1 to n minus 1 into delta R, because smallest value is nothing but minus 1. So taking minus 1 outside, it is nothing but b minus a. So the value is a minus b. Accepted? So if you calculate the upper sum, UPF, so whatever the partition you take, infimum value is, LPF value is a minus b and UPF value is b minus a, lower sum and upper sum. So if you calculate the lower integral, integral a bar to b f, it is nothing but a minus b. If we calculate upper integral a to b bar f, it is nothing but b minus a. Because for every partition, if we calculate LPF, it is nothing but a minus b. For every partition, if we calculate UPF, it is nothing but b minus a. Since a minus b and b minus a both are different, they are not equal, because a and b are different numbers. Because we are taking an interval, always a is small and b is big in the interval, whatever the interval you consider. So a minus b and b minus a both are always different, they are not same. Hence the function is not Riemann integrable, because lower integral is not equal to upper integral. Integral a bar to b f is not equal to integral a to b bar f. Okay? So the answer is the function is not Riemann integrable, because lower integral is not equal to the upper integral. Clear? Fine. So if it is noted by you, I want to take one more problem on this definition concept. Then I will wind up our session, and tomorrow we will meet with a similar kind of problems. So after noting, you please tell. Because with a short gap, I have started taking the classes. Thank you. Now let us take the problem that, just hold on a moment, I will take that. So let us take the function f of x is equal to x square on the interval 0, a. Now we are going to verify that whether it is Riemann integrable or not. If so, what is the integration value? And obviously the answer is known to us, because if we calculate integral 0 to a x square dx, it is nothing but a cube by 3. Accepted by doing our integration, the +2 formula. Now using the definition of Riemann here, theoretically you are proving that the integration value is a cube by 3 by considering a partition. Fine. Now let us do it. So usually we are considering n segments for a given partition. So 0 minus a minus 0 by n, if you consider, it will be a by n. Why I am saying that? I am going to write the partition as, this is delta r. The formula for delta r, subinterval length is b minus a by n. Upper value minus lower value whole divided by number of segments you are considering. So the partition is 0, a by n, 2a by n, 3a by n, so on, n a by n, nothing but a. This is the partition I am going to take. So is that clear how the partition is chosen here? Any questions? Usually you take n segments on the subinterval. So the length of the subinterval is divided with n. So a minus 0 by n. So a by n is nothing but subinterval length delta r. Usually we take equal subintervals, not different subintervals. So if you take any arbitrary subinterval IR, what it will be? R minus 1 into a by n, comma r a by n. How I have arrived with this conclusion? Because if you take the first interval I1, it is nothing but 0 comma a by n. If you take second subinterval I2, it will be a by n to a by n. If you take third subinterval I3, it will be 2a by n, 3a by n. So whatever the suffix is there, this suffix is coming here. Can you observe? So if you write IR, this R will come here, the previous number will come here. 2, 1, 3, 2, 1, 0. Is it clear how the rth subinterval is written? Fine. So you know the partition, you know the rth subinterval, you know its length. Now let us calculate LPF and UPF as it is. So let us calculate LPF. Since the function x square is the increasing function, so whatever the interval you consider, the first number gives the infimum and next number gives the supremum. So if you consider, let me say UPF value, let us say it will be summation r is equal to 1 to n mr delta r. This equals to summation r is equal to 1 to n, mr means the function value which is big in the subinterval you have taken. Since it is increasing function, in this subinterval, the first value gives infimum, the last value gives supremum. So mr is nothing but r square a square by n square. How I have taken? Because the function is x square. Substitute ra by n in the function. And delta r is nothing but a by n. So it is nothing but a cube by n cube into summation r is equal to 1 to n r square. Accepted? Please check. Right. So if you expand it, a cube by n cube into, so 1 square plus 2 square plus 3 square plus so on plus n square. So sum of the squares of the first n natural numbers, you have a formula, n into n plus 1 into 2n plus 1 by 6. Here it will be a cube by n cube into yes or no? Agreed all? Right. So n cube will be gets cancelled if you take n as common in the numerator. So it will be a cube by 6 into 1 plus 1 by n into 2 plus 1 by n. Please check, n cube gets cancelled. So what happened? I have arbitrarily chosen a partition P. I have calculated the upper sum UPF, and this is the value of the upper sum. Now what I have to do? I have to consider all possible partitions on the interval, and for each partition I should find the upper sum, and among all the upper sums I should take the smallest one. That's why the usual procedure is described as you are going to apply limit n tends to infinity to calculate the upper integral. So upper integral 0 to a bar f dx, because the interval is 0 to a, is nothing but limit n tends to infinity UPF. So if you apply limit here, it will be a cube by 3. Similarly, we will calculate LPF, and for lower integral, we apply limit n tends to infinity, and you will get a cube by 3 as well. Applying the same formula, sum of the squares of the first n natural numbers we will get. So lower integral and upper integral, both the values are equal, hence the function is Riemann integrable. The common value is a cube by 3, so integral 0 to a x square dx is nothing but a cube by 3. That is the conclusion. Okay. So whatever the function you take, any polynomial function, trigonometric function, exponential function, whatever it is, you are doing Riemann integration means you have taken a partition, you have calculated LPF, UPF, and you have calculated the lower integral and upper integral, and both are becoming equal. That common value you are taking it as integration value. If the integration values are unequal, then we say that it is not Riemann integrable. If the integral values are unequal, then we say that it is not Riemann integrable. Okay. So any more queries over that? Finding lower integral as well as upper integral there? To anyone? Please tell. Is it clear? Finding LPF and applying the limit, finding UPF and applying the limit. so that you are calculating the lower integral as well as upper integral. Now the interesting thing here is, if I have taken tan x, sin x, cos x on a closed interval AB, so taking a partition, calculating LPF, UPF, and calculating upper and lower integrals by applying limit n tends to infinity is a hazardous task. As far as the definition is concerned, whatever the function you are choosing on a closed interval, by means of integration, you need to do all this procedure. UPF, LPF, everything we are going to do. But as and when the complexity of the function increases, this procedure is very tedious. Agreed? That's why different results are introduced, so that based on the result, simply we say that the function is whether integrable or not on the given interval. That is the useful thing discovered by the results. Fine. So let us wind up our today's session here. If you have any other queries, you can ask, and tomorrow we will resume with the continuation of this concept by taking some problems and interesting results. You can ask if you have any other queries.